It is very hard for archaeologists to explain how that was done.
That's why I'm more interested not in how the Egyptians built the pyramids, but how the pyramids helped to build Egypt.
It is very hard for archaeologists to explain how that was done. That's why I'm more interested not in how the Egyptians built the pyramids, but how the pyramids helped to build Egypt. For generations, scientists believed they already knew how the ancient Egyptians cut granite. Copper tools, stone hammers, endless manpower, and decades of relentless labor. It was a story repeated in textbooks around the world. Then someone did something no one expected. They asked Grok AI to analyze the famous Aswan quarry. They expected the machine to confirm everything historians had believed for decades. It didn't. Instead, it pointed to patterns that many researchers had overlooked. Its analysis challenged long-held assumptions and raised a question that stunned everyone in the room. Because if that analysis is even partly correct, the marks carved into the granite may not be as easy to explain as history has long suggested. 20,000 workmen, 15,000 rotating in shifts, 12 hours a day. Was that really enough? Before we uncover what the AI actually found, take a second to subscribe if you enjoy documentaries that explore history, archaeology, and ancient mysteries with an open mind. It really helps the channel, and you won't want to miss what's coming next. So, what did the AI see? Stay with me, because once you notice it, you cannot unsee it. The Aswan granite quarry lies along the banks of the Nile in southern Egypt. For most visitors, it seems like an ordinary archaeological site, massive unfinished blocks of stone scattered across a silent desert landscape. Many tourists pass through in just a few minutes without realizing they are standing in one of the most debated locations in ancient engineering. But everything changes when you move closer. The rock itself begins asking questions that are surprisingly difficult to answer. The mystery starts with the material. This isn't soft limestone or fragile sandstone. It is granite, one of the hardest natural stones commonly used in ancient construction. Ranking around 7 on the Mohs hardness scale, granite is so resistant that even modern stoneworkers consider it demanding to shape. Anyone who has worked with it knows that cutting it requires tremendous effort, specialized tools, and exceptional precision. Keep that in mind, because it makes the markings across the quarry even more intriguing. Running over the granite are long, smooth, curved grooves that appear remarkably consistent. Instead of looking random or uneven, many of the cuts seem to follow graceful arcs, almost as though a single tool traveled across the surface in one uninterrupted movement. The grooves blend together with surprising regularity. There are few abrupt breaks, little evidence of chaotic impacts, and very little of the irregular pattern normally associated with repeated hand strikes. People visiting the quarry often react in exactly the same way. They pause. They look closer. Then they ask the obvious question: could these marks really be thousands of years old? At first glance, some observers feel they resemble machining marks more than the rough scars expected from simple pounding tools. Whether that impression is accurate or not, it is this first reaction that has fueled decades of debate. For generations, historians have offered a straightforward explanation. According to the traditional view, the ancient Egyptians shaped this granite using extremely hard dolerite pounding stones. Workers repeatedly struck the surface with these heavy hammer-like rocks, gradually breaking away the granite until enormous blocks could be separated from the bedrock. This remains the explanation presented in many textbooks today. The scale of the work would have been extraordinary. Some estimates suggest that around 20,000 laborers participated in quarry operations over time, with roughly 15,000 rotating through shifts so production could continue almost continuously. Day after day, workers may have spent long hours striking the granite, sometimes for months or even years before freeing a single massive stone. Viewed from that perspective, the theory seems reasonable. Enough time, enough labor, enough determination. History has shown that remarkable achievements can come from persistent human effort. But eventually, some researchers decided there was only one real way to evaluate the idea. Instead of debating it, they attempted to recreate it. Using replicas of the same dolerite pounding tools described in archaeological studies, experienced craftsmen repeatedly struck large granite blocks, following the traditional method as closely as possible. The expectation was simple. If the accepted explanation was correct, the experimental granite should begin developing marks similar to those seen in the Aswan quarry. That isn't what happened. The test surfaces developed irregular depressions of different depths. Some impacts removed large fragments, while others barely marked the stone at all. Chipping appeared around the edges, spacing varied from strike to strike, and the finished surface lacked the smooth, repeating patterns visible in many quarry sections. The outcome wasn't simply different. It differed in a very specific way. As the workers continued, fatigue naturally affected their rhythm. Slight changes in grip, swing angle, and striking force became more noticeable over time. Instead of producing greater consistency, prolonged effort introduced greater variation. That is exactly what we would expect from human motion. No matter how skilled someone may be, muscles tire. Timing changes. Small differences accumulate with every swing. Now, compare those experimental results with many of the grooves found at Aswan. Several sections display long sweeping arcs with remarkably regular spacing and an appearance that seems far more uniform than the recreated pounding marks. For some researchers, this contrast raises an important question. Does the traditional explanation fully account for every feature visible on the quarry walls? It is at this point that some investigators turned to artificial intelligence, hoping it could analyze the evidence without relying on long-held assumptions. Rather than asking experts for another opinion, they assembled detailed digital records of the quarry itself. Thousands of overlapping high-resolution photographs were captured and combined using photogrammetry, creating highly accurate three-dimensional models of the rock surface. These digital reconstructions allowed researchers to inspect every groove from virtually any angle and measure details with exceptional precision. The models were then analyzed using an AI system designed to compare surface patterns produced by different categories of tools. According to those researchers, the software wasn't instructed to favor any historical theory. Instead, it was tasked with measuring geometric characteristics and comparing them against a large collection of documented tool signatures. Across hundreds of individual grooves, the system evaluated features such as curvature, arc radius, cutting angle, depth, spacing, and overall consistency. For a human research team, performing that level of measurement manually could require years of work. For a computer, it is simply another pattern recognition task. And that objectivity was considered one of the experiment's biggest strengths. Unlike a person who may already have expectations shaped by years of studying ancient Egypt, the AI was intended to examine only the measurable evidence before reaching any conclusion. Human experts naturally approach evidence with years of training and long-held expectations. If they have spent decades studying ancient quarrying methods, they are likely to interpret new evidence through that familiar lens. An AI, by contrast, is intended to evaluate measurements without any attachment to a particular historical narrative. It doesn't know it's examining Egypt, doesn't recognize the era, and has no preference for one theory over another. It simply compares shapes, depths, angles, and patterns against the information it has been given. That was exactly the goal. Instead of beginning with assumptions, the researchers wanted the stone itself to guide the conclusion. When the analysis was complete, one figure immediately stood out. Across all 847 measured grooves distributed throughout the quarry, the overall variation was calculated at just 4.3%. At first glance, that number may not seem remarkable. From an engineering perspective, however, it immediately draws attention. No matter how experienced a craftsman may be, repeating the same motion hundreds of times inevitably introduces small differences. Every swing changes slightly. The angle shifts. The amount of force varies. Human movement is never perfectly identical. Because of that, variations somewhere between roughly 12 and 20% are generally considered normal during repeated manual work, and even values approaching 22% are not especially surprising. Humans simply aren't machines. That is why some researchers found the reported 4.3% consistency so intriguing. Take a moment to think about that. And if you're enjoying this deep dive into ancient mysteries and archaeological discoveries, don't forget to subscribe. It really helps the channel, and we've only begun uncovering this story. The AI noticed something else as well. It wasn't just the spacing between the grooves that appeared consistent. The entry angles showed a similar pattern. Many of the cuts seemed to begin at nearly the same orientation, almost as if every pass had followed a carefully controlled path. Rather than resembling the work of countless individuals, the overall pattern appeared, at least according to the analysis, to reflect an unusually consistent process. At that point, the discussion shifted from archaeology toward engineering. If manual work typically produces noticeably larger variation, why do these quarry marks appear so uniform? That question led directly to the next stage of the investigation. The tool comparison. Once the measurements were complete, the AI attempted to identify which known cutting methods most closely resembled the quarry marks. To do that, it compared the grooves against thousands of documented tool signatures, ranging from simple hand tools and ancient implements to modern industrial cutting systems. The traditional pounding stone explanation was evaluated first. According to the analysis, manually hammered surfaces tend to display irregular depths, inconsistent spacing, and constantly changing impact angles. The marks at Aswan, however, appeared considerably more repetitive in several measured areas. The system then expanded its comparison to modern cutting technologies. 3 categories consistently ranked among the closest matches. The first involved high-speed rotary cutting systems equipped with diamond abrasives, which are capable of producing clean, repeatable cuts through granite. The second consisted of abrasive water jet technology, where an extremely high-pressure stream mixed with abrasive particles slices through stone with remarkable control. The third was ultrasonic machining, a process that uses high-frequency vibration to create exceptionally precise cuts. The important characteristic shared by all 3 methods wasn't simply their ability to cut granite, it was consistency. Machines don't become fatigued after hundreds of passes. They don't gradually alter their grip or unconsciously change their striking angle. When properly calibrated, they can repeat the same movement again and again with extraordinary precision. According to the analysis, that repeatability was one of the strongest similarities between these modern systems and many of the marks documented inside the Aswan quarry. Each cutting technology leaves its own distinctive signature, and the AI compared every measured groove against those signatures individually. Up to this point, the project was simply an exercise in pattern matching. Then the confidence ratings appeared. According to the researchers, the highest similarity score corresponded to an industrial-style rotary cutting pattern, with a reported confidence of approximately 94%. That result immediately sparked debate. The analysis also highlighted another striking observation. Across hundreds of measured grooves, the estimated entry angle reportedly differed by less than 2 degrees. Imagine repeating the same motion hundreds of times in different locations while maintaining almost exactly the same approach angle throughout. Many engineers would consider that level of consistency extremely difficult to achieve manually. And this is where the puzzle became far more controversial. The modern technologies that most closely resembled the measured patterns, diamond rotary systems, abrasive water jets, and ultrasonic cutters, are products of the industrial era. No accepted archaeological evidence currently demonstrates that such technologies existed in ancient Egypt. That leaves two very different interpretations facing one another. One follows the traditional historical explanation centered on ancient stoneworking techniques. The other suggests that certain measurable features deserve additional investigation because they appear unusually consistent. Whether that difference reflects unknown ancient methods, limitations in the comparison, or something else entirely remains a subject of ongoing debate. The deep vertical shafts. There is another feature of the Aswan quarry that receives surprisingly little attention. Many visitors walk right past it. Yet for some researchers, it raises one of the site's most interesting engineering questions. Scattered throughout the quarry are narrow vertical shafts descending roughly 30 to 50 feet into the granite. Most measure only about 3 to 4 feet across at the opening. From the surface, they appear to be little more than deep holes. But looking down their walls reveals something familiar. Several of the same curved, repeating groove patterns seen across the open quarry also appear inside these confined shafts. Similar spacing, similar curvature, similar overall appearance. And that's where the practical question begins. If these surfaces were shaped primarily by repeatedly swinging heavy dolerite pounding stones, workers would have needed enough room to generate effective force. A full hammer swing requires significant clearance behind the body. Inside such narrow shafts, maintaining that range of motion would have been considerably more challenging. Exactly how ancient workers managed that task, and whether the traditional explanation fully accounts for every feature inside these confined spaces, continues to be discussed by researchers studying the quarry today. At first, this might sound like a minor technical detail. It isn't. The traditional hammer explanation relies entirely on one thing: momentum. To fracture granite with a heavy dolerite hammer, the worker must swing the tool through a wide arc. That movement builds speed, and the speed creates the impact needed to break the stone. Without enough room for that arc, the hammer loses most of its effectiveness. Simply pressing or lightly striking a granite surface with a heavy stone isn't enough to produce the deep cuts found at Aswan. Now consider the narrow shafts scattered throughout the quarry. These aren't open workspaces. In many sections, they're so confined that standing comfortably is difficult, let alone performing repeated full-force hammer swings. Surrounded by solid granite on every side, with limited space and significant depth, the environment would have been extremely challenging for manual quarrying. Yet the markings inside these shafts closely resemble those found on the exposed quarry walls above. The grooves display similar curves, similar spacing, and the same remarkable level of consistency. According to researchers who analyzed these features, Grok AI evaluated several factors simultaneously, including the width of the shafts, the hardness of the granite, the geometry of the grooves, and the amount of clearance required for a traditional hammer swing. The system reportedly concluded that using a back-swing-dependent tool inside some of these confined spaces would have been physically impractical because of the available working room. By contrast, a tool capable of applying force directly from the front, without requiring a wide swinging motion, could theoretically operate even within these restricted conditions. Whether that interpretation is ultimately correct remains debated, but it raises an interesting engineering question. The tighter the space becomes, the harder it is to imagine using a large swinging hammer. Yet the grooves continue uninterrupted. Physics doesn't change simply because a historical explanation becomes inconvenient. Looking beneath the surface. Everything discussed so far focused on the visible marks carved into the granite. The next stage of the investigation looked much deeper. When stone is examined under high magnification, details invisible to the naked eye often reveal how it was actually worked. Repeated hammer blows normally leave a very recognizable microscopic signature. Each impact creates tiny fractures that spread unpredictably through the mineral crystals. Under a microscope, hammered granite typically appears full of broken grains, stress lines, chipped edges, and countless microscopic cracks extending beneath the surface. Researchers studying samples from Aswan reported something quite different. Instead of widespread fracture damage, portions of the cut surfaces appeared unusually clean. The boundaries separating the carved groove from the untouched granite looked sharp and well-defined. Rather than appearing shattered, some areas looked as though material had been removed in a controlled slicing action. Engineers describe this type of surface as a shear pattern. Another surprising observation followed. Researchers reported finding very little subsurface cracking beneath some of the examined cuts. If repeated hammer impacts had created the grooves, deeper fracture networks might be expected beneath the surface. Instead, several samples appeared to concentrate their alteration almost entirely along the cutting boundary. The investigation became even more interesting at higher magnification. Some researchers described extremely fine spiral-like patterns running along portions of the grooves. These faint rotating traces appeared consistent with the movement of a tool traveling while continuously rotating. Even samples collected from different locations within the quarry reportedly displayed spirals oriented in similar directions. Heat provided another clue. Certain microscopic regions showed evidence consistent with localized thermal alteration. Instead of heat spreading broadly across the surface, it appeared concentrated into relatively small contact areas, something researchers suggested could resemble the friction produced by rapidly rotating cutting systems. The final observation involved tiny mineral particles. Among the microscopic debris, investigators reported finding grains of corundum, a mineral with a hardness of 9 on the Mohs scale that is widely used today as an industrial abrasive. Some reports also described carbon structures with characteristics that researchers considered diamond-like. Each of these observations can be debated individually. A clean shear surface, limited subsurface damage, fine spiral markings, localized heating, extremely hard abrasive particles. None alone necessarily provides a complete explanation. But taken together, some researchers argued that they collectively resemble the signature of a cutting process rather than repeated blunt impacts. The AI reportedly identified the closest overall similarity as an industrial-style rotary abrasive cutting process. In other words, according to that analysis, the granite appeared less like it had been broken apart and more like it had been machined. A timeline that raises new questions. As researchers attempted to estimate when various quarry marks were created, another unexpected pattern reportedly emerged. In several areas of the quarry, ancient red ochre paintings are visible directly on top of existing carved surfaces. That sequence is important. The grooves had to exist before the paintings were applied. Some researchers have argued that certain paintings may date to periods significantly earlier than Egypt's early dynastic era. If those dating estimates are correct, then at least some of the underlying cuts would necessarily be older still. That would place portions of the quarry activity within Egypt's pre-dynastic period, a time generally associated with smaller communities and comparatively simple stoneworking technology. To explore this possibility, researchers reportedly performed what they called a temporal precision analysis, comparing estimated ages with the measured geometry of the quarry marks. According to their report, the AI detected an unexpected trend. The grooves believed to be oldest also appeared, on average, to be the most uniform and geometrically consistent. By contrast, marks considered younger displayed greater irregularity and more closely resembled ordinary manual stoneworking. If supported, that would represent a surprising reversal of what many people might expect. Rather than craftsmanship becoming increasingly refined over time, the measured precision appeared to decrease. Researchers further reported that statistical testing indicated the observed relationship was highly unlikely to result from random variation alone. Whether future studies confirm, modify, or challenge these findings remains an open question. But if the reported pattern proves reliable, it would add another intriguing layer to one of archaeology's most debated engineering mysteries. One of the biggest assumptions we make about history is that technology always moves in one direction, forward. Early craftsmanship is expected to be rough and experimental, while later generations refine techniques until they reach their peak. But according to the interpretation presented in this analysis, the evidence at Aswan appears to tell a very different story. Instead of improving over time, the oldest quarry marks seem to display the greatest precision, while later work becomes progressively less consistent. If that pattern is genuine, it raises an extraordinary question. What if the earliest builders possessed knowledge or techniques that gradually disappeared instead of improving? Reading the stone. Until now, the mystery centered on one question: how was the granite cut so precisely? Then another possibility emerged. Some researchers began wondering whether the builders weren't simply shaping the stone. They may also have understood its hidden internal structure before making the first cut. Granite isn't perfectly uniform. Beneath the surface lie mineral bands, crystal boundaries, and naturally weaker zones where the rock separates more easily. Modern quarrying companies invest heavily in mapping these hidden features using ground-penetrating surveys, sonar imaging, and computer-based geological models. Those scans allow engineers to identify the easiest cutting routes before work even begins. Interestingly, several cutting paths at Aswan appear to follow these naturally weaker internal zones. If that observation is correct, it suggests the builders repeatedly chose routes requiring the least resistance, even though the internal structure cannot be seen from the outside. That may be one of the most intriguing aspects of the entire site. Using the right cutting tool is one challenge. Knowing exactly where to cut is another. Looking at the surface of a granite block reveals very little about what lies deep inside. Today we rely on sophisticated instruments to uncover those hidden structures. Yet some researchers argue that the ancient cutting paths seem to align with them surprisingly well. When Grok AI reportedly compared mineral mapping data with the quarry grooves, it found what researchers described as a meaningful correlation. According to the report, the system estimated, with roughly 88% confidence, that many of the cuts appeared to follow the stone's internal structure rather than random paths. Engineers sometimes refer to this approach as selecting an optimal cutting path, removing the greatest amount of material while using the least possible effort. That observation has inspired what some call the stone reading theory. The idea suggests that whoever created these cuts may have possessed a practical way of identifying the hidden architecture inside granite before cutting into it. Whether that interpretation is correct remains debated. But if it were true, it naturally leads to another question. If these builders were capable of such remarkable precision, why did they leave behind one of the greatest unfinished monuments in history? The unfinished obelisk. Among all the remains at Aswan, one structure captures almost everyone's attention: the unfinished obelisk. Still attached to the bedrock exactly where ancient workers abandoned it, this enormous monument is believed to be the largest obelisk ever attempted. Had it been completed, Estimates suggest it would have weighed more than 1,000 tons. Just imagining the project is astonishing. After all, investing years of labor into a fractured monument would hardly make sense. And if you enjoy exploring archaeology, ancient engineering, and history's biggest unanswered questions, don't forget to subscribe and turn on notifications so you won't miss our next deep dive into the mysteries of the ancient world.